present, Abhay was supposed to present this, but he works for our hardware team. He is our lead embedded engineer, and a lot of the sensor data that I would be talking about is actually mostly design. He is the one who has who does all the backend work for these for our device. We do the analytics part. So it's a very close collaboration that we have. And this presentation was also prepared by him. So there is no change in what he was going to present. I will be just presenting what he had planned for. So moving on, and make this as an interactive session. I will have a hands-on session also towards the end. So feel free to ask any questions in between the presentation. Okay. So what is sensor data? So So it is like, it's output of a device that that detects and responds to some type of input from the physical environment. For example, if you have, we do use a lot of temperature, humidity, pressure sensor. So it kind of detects and responds to any variation in temperature, humidity, or pressure. So for this talk, I will be focusing only on IoT sensors. And what are these IoT, what do we mean by IoT or Internet of Things? So it is actually a system that consists of connected sensors or devices that talks to the cloud through some kind of connectivity. There are various ways that the interaction to the cloud happens. In our case, in the device that we use at Fussell, we use it through SIM card, that nowadays all the telecommunication company, they have IoT based SIM card. So that is the technology behind how we communicate using our IoT data, our IoT device. And when I say cloud, think of cloud, it's like a server sitting somewhere and it is accessible to anybody who's authorization to that server. And that way, that if we want, we can then send that data to anybody sitting anywhere in the world. So it is now going to change. Like earlier, internet was used for only human to human interaction, but now this is bringing in a new era where the things is, if anything in the world can interact with any other thing. So for example, if we have our device where we are able to detect soil moisture sensor, and the same farmer has irrigation device, automated irrigation system from some other company, then using the data that our soil moisture captures, we can send an information or a trigger to the irrigation system of the irrigation company, and that will automate the whole irrigation process for the farmer. And that is how the whole automation, how IoT is going to make everything, reduce the manual labor and make everything automated. So there is a very beautiful line that Kevin Ashton, the father of IoT, said that it could turn the world into data. And that is what is happening. Now we are even if you have smart devices, any of the smart devices you have, it captures every information that if I have a smart vacuum cleaner, so it captures any information like how many times do I use a day, how many times it gets filled with dust, and and the map of my apartment, where it gets stuck mostly. And then using these data, they can improve, when you see all these electronic devices bringing in newer versions of their device, it is done using the data that is being captured on how consumers are using it and how they are consuming the product. So and it is also in our case, it is also like, a great way that we could reduce waste and increase efficiency. And so it is like IoT is being used now in every sector, whether it is transport, industrial, environment. Uh, I will be focusing and talking about the use case from agriculture, how we use sensor data for weather forecasting and how it is helping Indian agriculture. Um, so, what are the current core problems in agriculture? So then the whole idea of Fasal came into the initial problem that we observed was that growing a crop is not easy. It requires, plants are very susceptible to and very prone to any kind of environmental changes, and especially when you are growing a crop and that's your source of income, then it becomes more challenging. So, but unfortunately, most of our farmers, like the way they do farming, it is using guesswork. If they come from a traditional farming family, then they follow up what they have learned from their forefathers. But the environment is changing, the climate is changing, the varieties that their forefathers, ancestors used to grow, we don't grow it anymore. So what happening because of this guesswork, that leads to poor resource utilization. In the image here, I'm showing mostly water, because that is like one of the major challenge. Like Indian agriculture itself consume only like almost 70% of our water resources. The water use efficiency of Indian farming is around 38%, compared to 70 to 80% water use efficiency in a lot of Western countries. And we have a huge population, so that leaves very less water for domestic use. Water is not the only resource that is being overused or poorly utilized. Fertilizer, a lot of these chemical compounds that goes into farming, that causes land degradation and releases greenhouse gases, and it affects climate change. So agriculture on at Indian national GHG emission scale, agriculture contributes to 20% in greenhouse gas emission. And this, the irony is that agriculture is the one that is most impacted due to climate change. The uneventful rainfall that is happening in Maharashtra and around Western Ghats, it has going to cause a huge damage to the grape farmers there. This is the pruning season, and so immediately following pruning season, there was heavy rainfall events. So that's where Fasal comes into role. So what Fasal, our motivation is, our vision is that we are an IoT-based AI-powered platform. We focus on horticulture crops. We have started also working with some plantation crops. But what we do is we capture real-time data using on-farm IoT sensors. And then using that data, we develop models that deliver very farm-specific, crop-specific, and crop state-specific actionable advisories to farmers. And these advisories the farmers receive using our mobile app, or they can use the web app also. Currently, we work with a lot of individual farmers, but we also work with some major agri enterprises like Monsanto, Grover Zampa, Bayer. And recently we got a pre-seed funding of $4 million. So how do we do that? So we have you can say that Fasal product, you can divide it into two parts. One is our IoT device. It comes equipped with 12 plus sensors that capture data, all these important environmental parameters at hourly frequency. That data is sent to the cloud. And as I mentioned in the beginning, that for us, the connectivity works using SIM cards. We can latch onto any network, whether it's Jio, Airtel, whatever is the the strongest source of network. The SIM card can latch on to any network, and it sends this data to the cloud. Using this data, we develop our models, and then we deliver the advisory to the farmers on their phone in their preferred language. So we have almost 12 plus sensors that the Fasal IoT device has. So we have sensor to measure canopy temperature. We have sensors to measure canopy humidity, air pressure. We also have a rain gauge that measures rainfall. We have a weather station that also measures wind speed, wind direction. There is a leaf wetness unit, which is like a very important parameter for pest and disease prediction. Then we have soil moisture sensors, and there are two soil moisture sensors that comes with the device. One is at the primary root zone and one is at the secondary root zone, and they are very crucial for irrigation advisory. Then we also have a soil temperature sensor as well as a sensor that measures lux and solar intensity. So if you see, like in a nutshell, we any parameter that has anything to do with crop growth is what we measure. And as I mentioned, using this data, we provide different advisories to farmers. So what kind of advisories do we provide? So one is microclimate forecast, and the rest of the talk will be focused about that, like how we do microclimate forecast and how it is different than your other weather forecast. The other thing is we provide very precise irrigation advisory. It is not a general advisory. So the irrigation advisory that we provide, it depends on the type of soil that is there, the kind of crop they are growing, what variety they are growing, what stage the crop is currently at. And based on that, we provide think of it there is a model that is developed, and then it tells the farmer like at what point they need to water and how much they need to water. The other thing we do is we provide very early disease and pest alerts. And then based on the kind of farming they do, whether it's an organic farming or they are a commercial farmer, then accordingly we send what kind of molecules they could use to as a what kind of preventive sprays they can take. So early disease and pest management is very crucial to manage overall crop, optimize crop yield and minimize chemical pesticide usage. The other thing is the forecast that we provide, it is up to 14 days. So that helps in the farmers can use our application for crop activity planning, because many times they need to hire laborers for certain farm activities. So they can use the application for their crop activity planning. And because we have disease and pest management system also, so if they enter when they took the last spray, accordingly it will tell them that when potentially when is the next spray due, what could be the weather be for next 14 days, and then accordingly the farmers could plan. And finally, the application, the Fasal app, could be used also can be used by the farmers to manage their farm finances. So now moving on, I will be talking about about microclimate forecast, how we use sensor data for microclimate forecast. So a microclimate is different than and the way we do microclimate forecast is very different than what weather companies usually do. We are not a weather company. We are a crop intelligence company. So most of the weather companies, they capture satellite data, geo-satellite data, and using that data, there are complex simulation models based on thermodynamics and other kind of laws of physics, on basis of which they develop and further downscale their models. These are very mathematical models that they use. And the if I talk the definition of microclimate, it varies from other climate like macroclimate, mesoclimate, based on the size, the resolution, the spatial resolution of for which you do the forecast. So a macroclimate, you can say the climate of a larger region, say either an entire state or an entire country. So like, you know, you would hear that people say that, oh, India is very hot. So that's like, you know, that's a on a macro level that they talk about. We are in a subtropical region, so yeah, we are like, you know, a hot and humid. You could say that's what the climate or weather of India is generally. Mesoclimate, you could say, like, you know, if that's what, when you open up a weather app, the forecast that you see, it is for like, you know, at a meso scale. So that means when they give you a forecast, it is for a much larger area. So it could be either for an entire city, or maybe for a bigger neighborhood, or maybe like, you know, one major PO, post office area. So usually based on company to company, the application, the source, the weather forecast source that you are seeing, the size of that forecast spatial resolution for that forecast could vary from 5 to 100 square kilometer. So which means whatever the forecast they provide, it is on a general like, you know, 5 square kilometer range, or up to, it can go up to 100 square kilometer. As I mentioned, it varies from weather app to weather app. So what we focus on is microclimate forecast. So for a farmer, it is very important what is going to happen in its farm. And on an average, we use AI model, we use our IoT sensor data and AI to downscale this meso level weather forecast to 100 square meter resolution, which is around like, you know, 1 hectare. That's on an average the size of the farm that most of our customers have. So, and this microclimate, it is an interaction between, you know, your local topography, your landscape. So for example, if you are like, you know, an orchard farmer, then the microclimate will vary a lot based on the practices that you do, the kind of a topography you have. So on those characteristics, the microclimate varies. How we do this forecast? So it is a dynamic time series modeling where we feed, like as an input data, we take historical IoT sensor data, and then we use the local forecast, which, as I mentioned, it is at the meso level. So we take forecast data from multiple sources. That's the input for our model, and based on that, like, you know, we train our model on past historical data, and then like, you know, use separate model for, say, temperature, for different parameters. So we have separate model for temperature, we have separate model for humidity prediction, for wind speed and wind direction prediction as well. And I'm calling it a dynamic time series modeling because we have, in the backend, we have built like an auto training pipeline. So where this training happens every 1 month, because there is year-to-year change in the climate, in the average temperature, in the pattern in which the temperature works. So this training happens every 1 month, and sometimes it could be more frequent also, depending upon the variation that we observe. And it like, you know, it auto trains on these historical data. And why we keep training every 1 month? Because we keep getting newer and newer data. For, like, you know, more weightage is given to the local data and to the recent data. So when we are training, so when we train, we use like almost 1 year data, but more weightage is given to last 1 month data versus, you know, last 6 months data. And this model outputs forecast for next 24 hours, which is at like, that is an hourly forecast that that is shown in the application. And then we provide a daily forecast for the next 14 days. So there is temporal difference in the resolution. So a short range is more hourly, that we tell you what will be the temperature or rainfall or humidity for every 1 hour for the next 24 hours. Whereas in the daily forecast, we tell you what will be the minimum temperature, maximum temperature, or average temperature, what will be the total rainfall amount. So that's how the daily forecast works. So how do the whole process of data modeling is actually follows, it's very similar, whether you do microclimate forecast, whether you do soil moisture, or whether you do stock prediction. They follow a similar life cycle. It is that you first prepare your data, where there is a lot of pre-processing work, a lot of cleaning, imputation. So imputation is if you have missing data, then you impute for those missing data, then you do standardization. So basically a lot of the AI models, you need to standardize your data, you bring it to a scale of 0 to 1. Just to give, so that you don't give unnecessary weightage to some one feature versus the other. There is one hot encoding. So if you have all these models, they cannot take string or text as a input. So for example, in our with microclimate forecast, we use a feature called season. So if I put season as summer, winter, autumn, the model will throw me error. So one hot encoding, it does it converts summer as a feature, and it will say whether January is summer or not. So it will then the value will be either 0 or 1, where 0 is yes, 1 is no. And then in the data preparation, once we do the pre-processing, then we extract important features. I will provide in the resources how for time series, how the feature engineering differs. Then there is model training, evaluation, and validation. So given the time limit for this session, we won't, honestly speaking, we won't even get to the whole part of data preparation. So I will be focusing on the first part, which is the cleaning part. And the reason being, when you are working with sensor data, there is quite a lot of ways that a sensor could go wrong. And you could say that, rest of the process, like feature engineering, model training, evaluation, and validation, we spend our time only once in that. And then we automate the whole process. There are already automated libraries available, and it doesn't take, we don't spend more than 20% of our time in that. 80% of our time goes in pre-processing, because that is something we would have to revisit every time, every 1 month or every 2 months. There is a concept called data drift, where the way your overall data is distributed changes over time. So the pre-processing part is where we spend most of our time. If we start seeing any problem at the validation part, the first thing we come and visit is here. We rarely see that we have to go back and do any new feature engineering or anything. Once done, it is good enough for almost next few years. But pre-processing is something we have to visit every quarter, or if not every 1 month. So I will be talking, and we will have a hands-on session on data cleaning. So why do we need to clean sensor data? And that way sensor data are very this anytime you automate and automate the process of data collecting, there are a lot of things you need to take care if you want to develop a good model. So one is that there could be input errors. So for example, if I think transplantation date doesn't matter for microclimate forecast, but it could be wrong GPS coordinate could be added to the application. So usually when we install the device, you go and turn on the, so you download the application and you turn on your phone, and it captures the location for the where you switch on the application. It captures from the GPS of your phone. Now, quite a few times happens that the installation happens at some place. The the main farmer is sitting somewhere else, and they switch on their phone from their home or their some other office, and it captures that as the code as the location for the farm. That can then mess up your like a lot of prediction for the, especially when it comes to microclimate forecast. It is very important what region you are, for what region we are predicting. Depending upon the agroclimatic zone, the models differ, like the models are different. Sure, yeah.
What's the difference between this data wrangling and data cleaning?
So data wrangling means it actually captures everything, like where you suppose if you are taking data from multiple sources and you are transforming it into a format on which you can work upon and do analysis. That is part of data wrangling. Whereas data cleaning is like once you get it in the particular format, then you start the process of data cleaning, where you start looking for missing data, some unusual anomalies, outliers in the data, and you get rid of that. So
you use only data cleaning, or even you go for data wrangling also?
So it depends from case to case. We use data wrangling also, and so here also we because the input involves not only sensor data but also data from multiple local weather forecast. So in that case, we do data wrangling as well. But again, with data wrangling, we do it once. We create a data mart, and we are done. But data cleaning is something, unless we figure out that we need to use data from some other additional sources. But data cleaning and data pre-processing, the imputation and all, is something we revisit almost very regularly.
Thank you, Madhumita.
Yeah. So the other thing could be your sensors could be malfunctioning. Either they stop working, which is easier to detect and easier to fix for. But if they start giving wrong data, that becomes a problem, and that there should be we usually have initial checkpoints to make sure that we are not getting wrong data. But then we also do very detailed data analysis to make sure that, and I will be talking about that none of your data should be wrong. So for example, if suppose if I'm I have a device in Andhra Pradesh, and suddenly my sensor records a temperature of -10. That's unusual for that place. You don't see that kind of a temperature. And if it is like the peak of summer and it suddenly records 100 degrees Celsius, that's also again not possible. So there are definitely we keep some usual rule-based checkpoints to make sure that the value lies within a range. But beyond that, we also use advanced analytics to identify anomalies or wrong data that the sensors could capture. Then there are mangled data where if your data, the sensors is giving you data which is beyond its range. And
any specific algorithms?
Sorry?
Any specific algorithms you'll be using for that?
We don't use a specific algorithm for that. It's actually, you could say, an ensemble approach. So okay, we use multiple algorithms for that.
Okay. Okay. Thank you.
And and then the other thing is duplicates also. If your data has duplicated values, then you need to also get rid of that. So some of the examples are if like for example, in this case, you could see that there is a sudden drop in air pressure. So I think this was like, a common confusion that people have, like, when we hear in news that there has been low pressure recorded, and then that could cause to rainfall. Usually that low pressure, and always that low pressure that is being recorded is around ocean and sea level. So what happens, like, when cold current, water current, and hot water current, they meet, it causes a dip in pressure. But when it comes to air pressure, if you will never see this kind of a dip unless you, like, you're going higher in the altitude. At the same level, you shouldn't record this kind of dip, because imagine this sort of dip your body will itself will respond to it. Even the slight dip in air pressure that happens sometimes during rainfall or heavy thunderstorm triggers migraine in some people. So this level of dip will cause a lot more problem. And in air pressure, this is something went wrong with the sensor. The other thing is, like, with mangled data, like, what happens, as I mentioned, that we have some initial checkpoints also. So if the sensor records a very unusual data, as I mentioned, like, if the temperature for a place where the temperature never goes below 15 degrees Celsius, if it is measuring -10, -15, so we just remove that data. And that in the application, it might show you that no data is available, and it could be, and because nothing is getting inserted into the DB unless we do some imputation for that. And usually for the customer, we do not show them any imputed or any this kind of data. We use that only for modeling. If a sensor is continuously giving us wrong data, we just go and fix the sensor. We try to use the best quality of sensor and capture as much of real data. These processes, as I mentioned, this cleaning and pre-processing processes, we only use at the back end for developing our models. And the other reason, like, which is a very common problem in India, is network issues. Most of our deployments are in very rural areas, and due to very poor cellular network, we start seeing these kind of messages, that there is data loss, and unless they don't go and restart. So the way the device works, it has it can store data up to a certain limit, but if the data remains out of network for say X number of hours, then it will go to a sleep mode. And unless someone doesn't go and restart the device, it won't wouldn't capture data anymore. So that's because of which also there is initially we have done a lot of fix from the hardware end that has taken care of it, but still we do some data loss due to network issues. So why do we need cleaning? Pretty simple, like, if your data is bad, it will lead to, like, bad models, bad accuracy. So it is very crucial to feed the right kind of data. The quality of the data is also very crucial. The other thing is if we don't capture the right kind of data, it won't accurately reflect what is the actual real pattern in our data. There is always, as I mentioned in the beginning, there is data drift. With microclimate, we do observe it very routinely, that the nature of the data, the pattern of the data, it changes very dynamically. Due to this weather change, you will start recording at what level you are capturing the data. So if we are not 100% sure the kind of data we are capturing, it will lead to that what the algorithm will learn will be not correct. And most of these algorithms actually are built on the pattern that is present in the data, and learn what is the general pattern rather than like, a customized pattern. So it is very important that most of your data should be as accurate as possible. And that is why data cleaning, it is very time consuming, as I said, when a lot of people, young AI people, they join the team, they mostly have spent a lot of time working on these online competitions, hackathons, Kaggle, and where, they get very good quality data, and they just have to spend their time building the most accurate model. But in reality, when they come and work, they just realize that most of their time they're spending in data cleaning and data pre-processing, as someone asked, like, in data wrangling. And that is not like, the fun part, but that is actually the most important and crucial part of data modeling. So yeah, moving next, what are the popular data cleaning techniques? It is either you remove these data, or you can directly go and correct. If you are, suppose if a certain value has to be this, uh, then you can just directly go and correct that value. We do scaling also, like if for certain algorithms, it is like how you measure rainfall, how you predict rainfall, and what are you feeding into the algorithm. It depends a lot on how you're scaling your data. So sometimes we do scaling also. Then there is imputation. Like if you remove a data that is not correct, then there are approaches that you could impute this data. So there are algorithms also for data imputation, or you can use a mean average, which is like a normal mean median, which is like a normal way, a very simpler way that people do imputation. The other is like, you can flag certain data, and you could keep it in your DB, but when you are training, you don't use those flag data. So these are some of the techniques that are used for data cleaning. Next, I will share, like, we will be using Google Cloud for the hands-on session. I will share the data, the link to the data, and then if you all have a Google account, then you can just go to collab.google. I think it's just Google Colab. If you put it in, yeah, it is collab. Let me just copy this link. I am putting it in the chat. So you can go there and just sign in using your Google account. And if you are not familiar with Google Colab, it is an excellent resource to have. You don't have to, like, if you want to work on Jupyter Notebook or anything, you have to first install Python, then Anaconda, and set it up all in your system. Whereas for this, you don't need anything. It's a cloud-based server, and the GPU, you get access to GPU or high CPU. It's on queue basis. So if you don't have to do like a huge data analysis, or you don't have to train a huge model, then this is an excellent resource to have. It's very good for learning. It supports both Python 2.7 and 3.6. And the best thing is it comes already pre-installed with most of the required libraries and modules that we use for machine learning and deep learning. So you wouldn't have to install all those libraries. But if you try to set up a system, set up a Jupyter Lab, which is very commonly used IDE for machine learning or for using Python, you have to install each and every library individually. So for any new learner or anybody, like even I still use Google Colab for a lot of my personal projects. So click on the link. Let me share with you the data source also. Okay. So I will share the data link also with you. And you can just uh, add this data to your drive. And then we can move next to the whole notebook where we can start working on Google Colab. So once you go to Google Colab, you can, let me just show that once. Okay. Okay, so this will open up, like, there is an introductory page where you get to see what some basic about coding and all that. And there is a, here you have code and text. So first thing, click on file and click on new notebook. Okay. And it will automatically connect you, give you some kind of a runtime, connect you to some server. It takes usually few seconds, not more than that. So yeah, if you see, it will create a new text. You can name it whatever you want, and then you can start following the codes that I will be sharing here, showing here on the screen. Yeah, let me reconnect this. Are you all able to see my screen?
Yes, madam. Yeah.
Okay. So the first thing we will do is, like, because the data that I shared with you is in my Google Drive. So the first thing we will do is, like, mount the drive to the Google Colab. So this is the code to do that, like from google.colab import drive, and it will mount the, like, G drive from the content. So if you run this code, it will ask you to go to the account, and there will be an authorization code. If you sign in through your account, use the same account that you use to sign into your Google Colab. So it will give you this code, copy it, and then here in the authorization code, you just paste it and then hit enter. So what it will do is, like, so here in files, I'm not able to see my Google Drive. Yeah, but now once it is mounted, I now have access to my Google Drive and access to any data that is present in my Google Drive. Okay, so this is the, once you have, like, added this data to the Google Drive, we will be using pandas for next step. So definitely import the pandas library, and then mention the path of your file. So in my case, it is in my drive. So if you have just opened up the link, it will be in your shared drive. So for example, if this is your drive, then it will be, like, shared with me. So there is a separate, sorry, there is a separate for shared drive. Yeah. So your path will be, instead of my drive, you will say that it is in the shared drives. Or you can, like, just go, like for me, I simply went there and it is in this observations. You can click here and you can just write copy path and then paste it here in the path. So that will, like, that way it will give you the path of that folder. Where it is located. And once you mention the path, then there is a CSV file that I had shared with you, which contains some sensor data. So the next thing is, like, we will, yeah, read that data here. So you might be seeing that, I have already tested this codes because I didn't want to run into any problem in middle of the session. So yeah, next, this function dot head, I think you might by now be familiar with this. It's very commonly used. So that will show you how the first few lines of your data set looks like. Now, if you see here, here there is, like, date, then there is a this kind of a separator, /, then time, then /t, wind. So the thing is, if you by default use this function, read underscore CSV. So CSV is for comma separated version of file. So by default, it expects that your data, each column is separated by comma. So because here the separator is not comma, it is like, it has put all the columns as one column. So we will reread this and we will mention that, use the separator as /t. Otherwise, as I mentioned, by default, it will take comma as the separator. The other thing we see is how the date is parsed, right? So if by default, I will just pass read underscore CSV, this is a very weird format, because here it is like Wednesday and then the time and then and the date format is very different. So in that case, we do mention that there is a separate, we do say that, take date time by combining the date as well as the time and make one column of date time there. So this is what is parse dates does. And then there is another condition we pass is whether the day is first. Otherwise, by default, it will take, so if you see in US style, they write the month first, then the day, and then the year. Whereas we do day first, then month, then year. So we do say that it is day is first as true. And we know it from the way we store the data in the backend. And then we say that infer the date time format. Otherwise, it will take default date time format, which is year, month, and it will again read the date time with will give you error. And it has happened in the past with me. I didn't pass the day first, and it is it started reading the day as month, and it created an entire mess with the data. So yeah, then you can, now we will use the same function, but we will pass certain conditions, and then we will read again the data set, run this code. Okay, so as I mentioned, here it created a date time column where it combined the date and the time columns together. And now you start seeing the different columns, that what are the sensor data that it has captured. We have wind direction, wind speed, wind gust is also speed. Okay, I don't know what exactly wind gust is measuring. Then temperature, then dew point, what it feels like, all that. This are various data that has been captured. Next is let's we can start removing any duplicates. So for example, here I don't see any duplicates, but in case if for the best way to find a duplicate will be if we have two entries for the exact same date time, not the date, but both date and time. So in that case, we can use the function drop duplicates, and we can say that used or it will start seeing for duplicates with this function. It will start seeing for duplicates if two date times are present, if the same value for the date time are present or not. And then we pass that keep the last value. Because sometimes what happens, if a sensor, there are certain error check and fault tolerance inbuilt within the hardware also. So what it does is if the fault tolerance system identifies that what it sent is a mistake, it will again send the data for the same time. So it is usually the data that is entered the last is the most accurate data. Okay, then the next thing we do is we sort the data. We sort it as per the date time. it makes the reading easier also. And then we, because all our analysis, everything will be on the basis of date time, we set date time as the index. Like we don't need this 1, 2, 3, 4 as the index. We're going to do that. So if you run this code, you will see that that index that you had of 1, 2, 3, 4 is gone. And instead you have now date time as the index. And then all the other values are here, and it is sorted also. So this data is every half an hour. It is captured every half an hour. So the frequency could vary from sensor to, now we follow 1 hour frequency, but there was a while when we used to follow from 15 hours to 2 hours frequency. The other thing that could be done is, like, as I mentioned, that if you have these kind of strings, and if you try to input in your algorithm, it will throw you error. So in that case, we want to convert the wind direction to the radian value. And here I'm using a dictionary where, like, north represents 0 radian. So it ranges. So usually when the wind direction is there, the radian, the wind, the sensor for wind direction, it actually measures it in degrees or radians. And it for north, it will be like, there will be a range. It will start from, say, 0 to X, then something like that. So we took the minimum value for different year, and then we just created a dictionary. So in that case, if we say that, in this wind observation, the wind direction is like, wherever there is what this code is doing is actually, wherever there is a north, it will replace it with 0. So now it will convert it into a numerical value, because it gets easier that way. Otherwise, there are, I think, 14 or 16 wind directions that you have. Maybe I'm wrong, whatever. So you will have, there, as I mentioned, there is an option of one hot on encoding. So where you could say that whether it is east, northeast, or whether it is southwest. And so then there will be a column for each direction. That will unnecessarily increase the size of your data. You will add unnecessarily multiple columns, which is not required. So you can simply convert it into numerical, and it makes sense also. No sensor measure it as east or west. It measure it as either as in degree or radians. So this is one way, as I said, that you can directly, this is the part of cleaning where you can directly replace value. Because we know what north means, what northeast means. So accordingly, we can do that. There is other thing also, that you can select a subset of the data. And like, if you want to see a slice of your data, that see how does it look, you can do that. Like, for example, here, I want to see data from 1800 to 1806 rows. And in that case, so this is based on, like, it's not like I knew that there is a problem in this row. There are different ways you could find whether your date time is at the right frequency or not. But this is like, this is a simpler way to show it. So what I see here is that, there are, when we remove date time, so this pretty much is actually a duplicate, because there is just 3 minutes difference, and we are more interested in a 30-minute frequency. So for example, if I want to forecast my data at 30-minute frequency, I would want all my date time here would be at 30-minute frequency also. So, but here, if you see, there is like, here there is a 3-minute frequency, then there is something like at 11th minute. We don't need that. And if the way time series modeling works, if I want to get output in 30-minute frequency, I have to give input in 30-minute frequency. So for example, in this case, I want my date time to be in 30-minute frequency. I can just simply do that, like, make all these, I could change the name of this table now, like, make it regular observation. And I say that take this data and change the frequency to 30-minute. And if I run it, it will then, like, give me the same data point, Now see the road numbers changes because there definitely are other values also that were not in 30-minute frequency. So what it usually does, like by default, if you do not pass anything, it will take the mean. So for example, this is, it will take these two values and just take a mean of it. Or sometimes it will just take like, the first value and remove the second value. So I think in this case, it just took the first values and removed the other value here because I don't see this to be a mean of it. So this now we have like, fixed it at 30-minute frequency in this case. And the other thing is also like for like, to figure out other issues in your data, you can then start plotting your data. So in this case, I am like, plotting like the first 500 rows just to see if there is any abnormality in my data, if there is any issues. And it gives you a very good visualization that what the issue could be. So can anyone tell me like what, if they can see what are the issues here in this data? Any guesses? Hint, I'm seeing a very clear issue in wind gust, the orange line. Are you all able to see my screen or am I going very fast? Okay, no guesses then. Yeah, so what the issue here is, like as I give you one hint that for wind gust, you see there are some missing values. You see also for wind speed. And I think in the data also there was like these NANs, they are actually nothing but missing values. So the next thing will be like, that we have to do some interpolation. And as I mentioned that there are different ways that you can do data imputation. One is that, like it take last nearby, the like, the last few datas and just replace it. Like here I say that replace the data at 2 o'clock with 67.5. If the data here is missing, then see the data below it and replace it with that, because it is anyways in half an hour and it varies from case to case. Here we can use that. Usually temperature, humidity, wind speed, it doesn't vary a lot within half an hour. But it won't be right to do it for rainfall, because sometimes you get a heavy rainfall and then within 15 minutes it is gone. So if you start imputing like, for rainfall, that this might not be right approach. But for most of the other parameters, you can do this kind of an imputation. So here I am saying that, that take data from both the sides and just impute it with that. Yeah. And if I run it, so now for wind direction, what it has done is like it's just taken the previous row value and imputed it. And it is fine if you have like, say data missing for 1 hour, 1.5 hours. Beyond that, we don't do that. Because if you have data missing for 4 hours, within 4 hours, there is, forget even 4 hours, depending upon the time. Suppose it is at noon, usually after 2 o'clock, there is a change in temperature in most of these parameters. So we don't go beyond 2 hours. If more than 2 hours data in a series is missing, we don't do the imputation. We actually remove that data from our training. So you do this imputation that takes care of your missing data. And now if you plot it again, you won't see any missing data here. So that in short, like of how we do like, basic imputation. I think I also covered direct removal and like, basic on data imputation. We didn't do any flagging here because we pretty much are like, removing whatever data that is inaccurate. We also did like, we looked into how to remove duplicate data. So that sort of covers this session. The next thing is I will share this PPT with you all. I have linked resources. Some of like these are very not very long articles, but like short articles on how time series forecasting works. The next steps. How time series forecasting is different from other forecasting. Then what kind of feature engineering is done. Then an example. So if you go through this article, it will mostly be doing an univariate where there is a date time and one factor. So for example, in the data I showed you, there is date time and there is only wind speed. So that's an univariate forecasting. But we know that wind speed is just not dependent on wind speed. It is dependent on difference in pressure, temperature, and all that. So for microclimate forecast, what we do is a multivariate time series forecasting when you have a lot of other external variables. So there is an article also on multivariate time series forecasting. And in the end, I have a Medium article from our Fasal page where we talk about like why exactly we build an AI-based weather forecasting. So as I mentioned, it's different from other weather forecasting. What we do is a microclimate forecasting. So that ends the session. If you all have any questions, then I would be more than happy to answer your questions. There is a question of using PhilNA. Is it Dr. Shankar, can you elaborate?
Yeah, I just wrote it just for filling up the missing data. You can use any instead of using NAN, NAN, you can replace it with no data, or you can replace it with the necessary data. We normally use the function fill now.
Oh, okay. Yeah. There is a PhilNA. Yeah, you can replace with that. So when we didn't, so yes, if you want to only fill your NA values, then that is an option. Definitely, that is an option, and they also have the option of taking a mean, average, median, or last two the previous row or the the successive rows data. Can we use any learning method to identify the missing sensor data collected? I'm not sure what do you mean by any learning method, but what we have used in the past for imputation, it ranges from one very common example that is used is the KNN model, which is nearest neighbor. It looks for similar data and you mention how many neighbors to look into, and then accordingly it fills in the value. But we have also used Bayesian optimization, regression, and if depending upon the data, sometimes we have also used deep learning approaches. So yeah, in a way, you can use any learning method to identify that itself is a prediction problem. So first you do use a model to fill in missing values, and then on that data you develop and train and develop a model. Any other questions for me? Okay. Thank you, Rana.
We request audience, like, is there any queries? You can, yeah, I guess like.
Thank you, Dr. Shankar, and thank you for your questions.
Like, I hope this is answer. Like, can we use any learning method to identify?
Yes, we can. I think, yeah, we can. We have also used a lot of various approaches, and now Python has also an inbuilt library where you can use random forest, Bayesian optimization, different approaches that you can use for imputation. Deployment of sensors. Can you elaborate a bit on, like, what do you mean by approach? Tahsin, right? I didn't understand your question. Oh, they don't, like, you know, the sensors are, it comes as a integrated part of our device. So with the recent, we call it Fasal Kranti, the most recent version of our device. If you can, you could, like, you know, let me see if I can show you. So it is pretty much like, you know, it comes as a, what I have shown here in this. Yeah. So this is the device here. But this is like an older version. The newer version is very easy to, so we ship the device, and it already has the sensors in it. But in the older version, it used to take, like, you know, close to 30 minutes to 45 minutes to install this entire device. And you know, so that here are the wind speed, the rain gauge sensors. Then here you have the main unit that has the temperature, the BME sensors, then the leaf wetness and all that. So it used to take a lot more time, like, you know, 30 to 45 minutes to install it. But now with the most recent version of our device, it is actually just click and play. It hardly take 5 to 10 minutes to install. Everything is already pre-installed. So all you have to do is just put it, just put the device in your farm, in your location, and the soil moisture sensors are also already installed. You just have to extend the pipe or the this BME sensor so that it is at your canopy height. But it is very easy to install now. Yeah, most welcome, Hassan.
If no doubts, like but NPK sensors, madam, there is a query. Like,
Oh, okay. No, we don't use NPK sensors. We have been, like, you know, so this is the link to the presentation if you want to access the resources that I shared. So no, we don't use NPK sensors. The device only has the 12 plus sensors that I showed during the presentation. We haven't had any like, in our experience, we haven't come across any reliable NPK sensors. Any other questions?
audience, I think if no doubts, like, okay, audience, madam, I think I think it's fine. Like, so if on any doubts, you can either type or you can unmute yourself and you can ask your question anyway. So thank you, madam. Thank you for your valuable time and sharing your knowledge and experience with all our participants. And we are very grateful to have you. And I thank you especially as a to accept as a last minute thing to go ahead with the session. And I thank you personally for that. And thank you so much. And we would like to collaborate with you in future. Thank you.
Sure. Thank you so much.
Sure.
Thank you.
Yeah.
You all enjoy the rest of the sessions.
Sure. Of course, madam. And of course, we enjoyed this also.
Thank you.
Yes, Unnikrishnan, please, you can proceed.
Yeah. Yeah, thank you, madam, for this wonderful session. So this was our 12th session. we are closing it for the day. So tomorrow is the last day for the faculty development program. So just reminding you on those sessions tomorrow. So you have we have 2 more sessions, and then the third session will be our valedictory session.
Just Unikrishan once, like regarding tomorrow's session, I just want to put some word to audience. Like tomorrow, our online test will be between 2:30 to 3. Online test will be it will be scheduled between 2:30 and 3:30. Okay, and then possibly from 3:15 or 3:30 onwards, our valedictory function will be there, and from there we will conclude our FTP. So all of you, please kindly note. Third session there will be an online test and your valedictory also. So that is kindly note of that. Yeah, that is fine.
Yeah. So that's it for the day. So we are closing it now for this day. Tomorrow at 10 o'clock we have our 13th session for the program. Okay.
Thank you, Dr. Madhumita, and
Thank
you
you.
all. Yeah, thank you all. Yeah.